This is lecture 3. This is also a kind of a refresher lecture, right, with of our UG concepts, which will be necessary in this course. So this is kind of the last of the refreshers. So in this lecture, we will revise our concepts on Fourier transforms, right, and how a signal propagates through an LTI system, and what are the analyses that we need to be aware of, right? So if you recall, in the previous lecture we talked about Fourier series, right, and we talked about how a periodic signal, or rather we looked into how a periodic signal can be broken down into a summation of exponentials, and what is the and how do we go about analyzing those, right? How do we go about analyzing those exponentials in time and frequency domains, right? So in this lecture we will do the brother of Fourier series, that is Fourier transform, but we will not jump into Fourier transform as is. I'll try to motivate as to why a Fourier transform was necessary in the first place, but the motivation will be from the perspective of signal processing, which will be necessary going forward in this course also, right? So let's begin. So let's say I have a linear time invariant system, right? We have a linear time invariant system. So firstly, what I mean by a linear time invariant system, note that it has two things. It has linearity and it has time invariance. Now, what is linearity? Linearity is nothing but if I say that I have an input, that is VIT, and the output is V naught T, the linearity dictates, right? So if input is VIT and output is V naught T, so linearity dictates that if I multiply VIT by some constant alpha, the output will also get multiplied by the same constant alpha. Note that alpha is independent of time, right? If I scale the input by a certain factor, the output will also get scaled by the same factor, right? And there is another property we are aware of, that is that of superposition. What is that? So if let's say the input is VIT, output is V naught T, and I say the input is, let's say, Vi2T, then the output is, let's say, V naught 2T, right? So these are two different observations, two different experiments, right? Or let's say the input is beta times Vi2T, then the output will be beta times V naught 2T. And then what do? I say that I apply the input to be equal to alpha times VIT plus beta times V naught T. So the output will be basically the summation of the outputs in either of those two cases, right? So this will also be alpha times V naught T plus beta times V naught 2T. So I made a mistake here. So this should be here, right? So this is as far as the linearity part of it is concerned. I mean, we know that, I know you know, but it is just to tie the threads together. So this is as far as linearity is concerned. So this is impact of linearity, right? And what is meant by time invariance? What is the impact of time invariance? So in time invariance, what we are essentially saying is, let me just write time invariance. Let me not like linearity. Let's say this is time invariant. Okay, so the input, let's say, is again some VIT, and the output is, let's say, V naught T. So if I now, time invariance is essentially saying, it means that if input is shifted in time by certain fixed interval, let's say input is Vi T minus T naught, right? So output will also be shifted by the same time interval. So output will also be T minus T naught, right? So if I essentially have to sketch these, this means that if VIT was, I don't know, maybe VIT was a step, and V naught T was maybe something like this. So if VIT gets delayed, so if VIT gets delayed, then the V naught T will also get delayed, and it will keep the same shape and size and everything, right? Just that it will be a delayed version, right? Simple concept, but extremely powerful that for analysis purposes, as you will see shortly, right? Okay, fine. So now, if we know this, then we also know that how do we characterize an LTI system? We characterize an LTI system from their impulse response, right? So what is an impulse response? We characterize an LTI system through its impulse response. And what does it mean? It basically means that if I apply a delta Dirac function at time t equal to 0, if I apply a delta t at, right, so the output will have certain shape. I don't know what the shape will be. It is particular to the system. Maybe its shape is like this, something like this, right? Some arbitrary shape, and let's call this shape h of t, right? This becomes a definition of a system per se, right? So if I apply delta t, what will the output look like, right? So now the question is, why do we bother about delta Dirac function? Because delta Dirac function is not an actual function, not practically realizable function that you can apply to any system, right? So why do we at all characterize a system with an input which we cannot ever give, right? The reason we do that is because it's a very handy mathematical tool, because just like any signal can be broken down into summation of sinusoids, if any signal can also be broken down into a summation of impulses, right? What do I mean by that? So let's say I have a signal. VIT, and the signal can be anything, something like this, right? And it goes from time t equal to minus infinity to time t equal to infinity. And this is the t axis, right? So let's say at some time tau, right, I say that I mark out the point of this signal, right? And I find out this value. This value will be what? This will be nothing but Vi tau, right? Okay. So if I now look at a very small sliver, right? If I now look at a very small sliver of around tau, that is tau plus delta tau, right? If I look at this signal around this very small sliver of between tau and tau plus delta tau, I can effectively say that if, as long as delta tau tends to 0, I can effectively say the strength of this signal, right? I can effectively say that this signal at this point, right? So signal at tau can be expressed as Vi tau times delta tau times delta t minus tau, right? Note that why can we express this signal in this format is because of the unique property of your delta function. That is, if I integrate delta t, right, over dt, that is delta tau, and delta tau tends to 0, right? If I integrate this, I get 1, right, from, let's say, t minus 2, or rather 0 minus 2, 0 plus, right? So this is a unique property, right? So essentially what I am saying is that if I define the sliver, right, if I define the sliver in this way, then I can basically get back the value of the function at any point of time by simply integrating this sliver between the points that I want, right? That's the motivation. Now, why this is useful? This is useful because I can now get back the entire signal, right? I can get, if I am able to express this input signal as essentially summation of so I'm probably going ahead of myself. So let me take a step back and say that. So what is this telling us? This is basically helping us define the function, define the signal within the small sliver of tau and tau plus delta tau. Now, if I want to define the function for all t, right, all I have to do is to vary tau from minus infinity to plus infinity. Then this sliver is going to move from minus infinity to plus infinity, and the sliver will move along with the weight of the function at each point of tau, right? So essentially, which means that I can then therefore define VIT, right? So now you see that if we can now express any signal as summation of delta functions, right? Summation of delta functions, and the weight of the delta function is essentially the value of the signal at that tau times delta tau, right? So if I express this in this format, and if I know the impulse response of the system, then I can basically find out the output of the system for any input, right? So then what should we do? We are basically saying that, hey, I know that this is an LTI system. I know that if the input is delta t, right? So the input is, say, delta t. So the output, let me draw it in a different color. The output is probably like something like this. If the input is let's say delta, it's shifted, right? If the input is shifted in time, what will the output be? Output will also be shifted in time. If the input is scaled in time, right? Let's say I scale the input by -1, right? If I scale the input in time, what will happen to the output? Output will also scale in time, right? And so on, right? So now, which means that we have a magic wand, right? Because I know that any input is basically summation of delta Dirac slivers, and I know that for each sliver, the output is essentially impulse response, delayed and weighted, right? So then I can also get the output back as long as I know the impulse response of the system. That is why one of the reasons why impulse response is a very important mathematical tool, even though we cannot generate an impulse to get the impulse response physically. Okay, so So now let's close the loop here and then see what will the final output be. So which essentially means that, so if, again, let me write it out. So your input is, so VIT is essentially, let me write it in terms of summation, and then I will make it integral, then it will probably make more sense. VIT is essentially VI tau delta t minus tau, right? So for every delta t minus tau, I am getting, so delta t creates h of t, so delta tau creates h of tau, and delta, this is delta t minus tau, delta t minus tau is creating h of t minus tau, right? And what is the weights of each of these t minus taus? It is basically the impulse, right? It is basically the impulse is weighted by this factor, correct? So your output will essentially be, this will create ht minus tau, and ht minus tau will get weighted by the strength of the input, and the strength of the input is Vi tau delta tau, right? And if I express it in terms of integrals, so your V naught t will end up becoming this, right? So this will delta tau. I mean, if I do not impose the constraint of causality, and I can say that ht of tau, ht also goes from minus infinity to plus infinity, I can basically say that this goes also, limits are from minus infinity to plus infinity. Okay, so essentially this becomes more formally written as Vi tau ht minus tau t tau V naught t. Okay, so this is again a very well known famous concept, but I wanted to harp on this because later at the fag end of the course you are going to see a more generic version of these concepts. Yeah, we call it linear periodically time varying circuit. So at that time it will be useful if we remember how the output of an LTI system came about, right? We'll start again from here when we go back, when we start the linear periodic time varying circuit concepts. Okay, but that is for another day. Let's continue with whatever we have been looking into, right? So fine. So now we have got an output for any arbitrary input as long as we know the impulse response. But the question is, so what? I can also, I mean, in the previous lecture we were talking about giving a complex exponential, right? Input is a complex exponential. If we talk about sinusoidal steady states where the input is a sinusoidal signal, right? So now we are talking about a case where the input is an impulse. But the good thing about a sinusoidal situation is that I can apply a very clean sinusoid. It's practically doable. Impulse is not practically doable. It's a theoretical construct, right? So what's the relationship between an impulse response and a sinusoidal steady state response? If I can connect those two, then we are kind of done, right? So that's the goal for the next few minutes. So it's pretty simple. Let me write it out separately. So again, so this is an LTI system having an impulse response h of t. That is, input is delta t, output is h of t, right? So we also know that. So if input is VIT, so output is minus infinity to infinity. Vi tau, tau is the running variable, h of t minus tau b tau, right? T is the time of observation. So if input for sinusoidal steady state, we have to apply an input to be a complex exponential. We can also apply sinusoid, but I know the sinusoid is basically sum of two complex exponentials, right? And since it's a LTI system, I can again add them up. So I will basically apply one exponential at a time, right? That's the whole idea. So if the input is, let's say, PIT is equal to e to the power j omega naught t, right? Your output is, or let me just say j omega t, where omega can be any frequency. Your V naught t becomes minus infinity to infinity e to the power j omega t h of t minus tau d tau. And if I do a variable change and say that t minus tau is equal to some eta, let's say, so then this becomes h of eta, then d tau basically becomes negative d of eta, but again the integration signs limits will also flip, so I'll keep it as d of eta. This becomes minus infinity to infinity. This becomes e to the power j omega sorry, this is tau. So tau is essentially t minus eta, right? So note that here I can take the e to the power j omega t out because it's not a function of d eta. So this becomes e to the power j omega t minus infinity e to the power minus j eta t h eta t eta, right? So, eta. Okay, so now this is the function of omega only, right? So which means that your v0t becomes e to the power j omega t times some function, I call it h of j omega, right? So what is it saying? It is basically saying that in an LTI system, important disclaimer, it has to be an LTI system, not a linear system. It has to be a linear time invariant system. In an LTI system, if an input is e to the power j omega t, the output is essentially a scaled version of the same input, right? All it's saying is that it's because basically output is e to the power j omega t times a scaling factor. Note that this is only a scaling factor because this is not a function of t, right? It is a function of omega, right, but not a function of t. So the output is a scaled version of the input, right? And this is only for the special case when the input is e to the power j omega t, not for any good inputs, right? I mean, case in point is if you give delta t, you are not getting a scaled version of the delta t at the output, right? So it is only for an LTI system when you have e to the power j omega t, the output will be a scaled version of a complex scaled version of e power j omega t, right? So note that h j omega is a complex number, right? Because it's basically this integral, right? It's basically this integral. So I can basically write, so what is this h j omega? Is basically you can write any variable here. This is basically the Fourier transform. This is the well-known Fourier transform integral. This is the Fourier transform of h of t, right? Okay, and I'm sure you know how to make Fourier transforms of, I mean, what is the Fourier transform of delta t, u t, and so on, e to the power minus at. I mean, those are something that we learn in our UG courses. This is also we learn in our NG courses, but this is relevant directly to our to what we are going to do. So that's why I took the time to revisit these concepts. Okay. Now again, just for the sake of clarity, by definition, h of j omega is equal to output, whatever is the output, divided by the input when in the input is e power j omega t, right? So when the input is e power j omega t, not any old input, right? Okay. So having said that, again, there is another important disclaimer. I should also point it out that h of j omega is not equal to output divided by cosine omega t. Right? H of j omega is not the response of the system when a cosine omega or a sine omega is the input, right? So h of j omega is also called the transfer function of the system. Also called the transfer function. But you should always keep in mind it is not the response of the system when a cosine omega t is an input or a sine omega t is an input, right? It is related to that, right? The next thing is, for us to show is how is it related. But note that it is not the same as saying the response of the output is not the same as when the input is cosine omega t or sine omega t. A transfer function of the system is basically the output that is scaled when the input is a complex exponential. Okay, fine. So what would be the output if the input is cosine omega t? So if VIT is cosine omega t, that is half of e to the power j omega t plus e to the power minus j omega t, then it's simple, right? So the output, I know that your V naught t will be half of, if the input is e power j omega t, what is the output? It is basically h of j omega e power j omega t, and if input is e power minus j omega t, what will happen? So again, this is a complex exponential only, so the output will be whatever is the omega will come in. This you have negative omega, so you get this, right? Okay. So if I say that, let's say your h of j omega has a real part hr and an imaginary part hi, right? And in a special case, I say that h of minus j omega is equal to hr minus j of hi, right? Which is true for any real system. And then I can basically write this v naught t to be equal to half. Yeah, so basically e to the power j omega t and e to the power minus j omega t will club. So I will, let me write it out fully. So I will get hr e to the power j omega t plus e to the power minus j omega t plus jhi e to the power j omega t minus e to the power minus j omega t, which essentially means that I get hr cosine omega t plus jhi sine omega t, which boils down to magnitude of hr square, magnitude of h of j omega, that is under hr square plus hi squared cosine omega t minus tan inverse hi by hr. Now what is this? This is nothing but magnitude of h of j omega, and what is this? This is nothing but the phase of h of j omega. Sorry, I made a mistake. This will be plus. So basically, your v naught t, when input is cosine omega t, is equal to mod of h of j omega, mod of the transfer function, times cosine omega t plus some phase where phi is basically the phase of the transfer function, right? Tan inverse hi by hr, right? So note that what is it telling you? It's basically telling you that if you give a cosinusoid waveform, right, and then the output will be a scaled version of the cosinusoid, not only the scaled version but scaled and shifted, right? That's the difference between applying a complex exponential and applying a real cosine signal, right? So that is why I mentioned 5 minutes back that your transfer function is not the same as the output when you apply a cosinus. It's not a scaled version of the output when you apply a cosine wave. The scaling factor will only give you the magnitude part, right? But the shifted version, the shifting part, will give you the phase part. So you can still get back the full transfer function, right? You can get back the full transfer function if you apply a cosinusoid, which is a real signal, unlike a complex exponential, right? You can get back the full transfer function, but it is not simply saying that it is not simply the scaled version, right? It is a scaled and shifted version, and the shift is important because the shift translates to the phase. Okay, so now why am I spending time on this? The reason I'm spending time on this is because sinusoids and cosinusoids are integral waveforms in any RF subsystem, right? So we are going to have LTI system, and sometimes you see we are not going to have LTI systems, but you are going to see we are almost always giving sinusoids and cosinusoids as the input, and we have some transfer function of the system. Now, given these conditions, we should be very clear as to how the final output should look like, right? So if I take an example for, so now we can give some real life examples. Let's say I have this classic RC circuit, which everybody is so familiar with. So VI, RC. What is the transfer function of the system? I mean, everybody can do it with their eyes closed. I'll not write it down. I'll just plot. We know the transfer function of the system is something like this. This is a low pass filter, right? So this is the mod of H of j omega. And what is the phase? Phase will also be probably something like this, right? So what is, if this is omega, this is omega. So what is at omega equal to 0? What is H of j omega? Omega equal to 0 means capacitor is open circuit. So whatever is the input is the output, right? So this is essentially 1. What is the phase? Phase is also 0, right? So let me write it down. Write down the full transfer function. So V naught t is essentially H of j omega e to the power j omega t. Omega t, if the input is e to the power j omega t, H of j omega is equal to 1 by 1 plus j omega RC. So note that I took a conceptual leap and I didn't show you how we come up with this, but again, the assumption is that we have all done this type of circuits before, so we'll not get into that level of basics. Okay, so if this is the case, right? So what is mod of H of j omega? That is what you see. So mod of H essentially 1 plus 1 by the root omega square r square c square, right? So at very low frequency it's 1, at very high frequency it goes to 0, and so on and so forth. Similarly, what is the phase? Phase is essentially tan inverse of, phase is essentially minus tan inverse of omega rc. So basically at omega equal to 0 it is 0, at omega to infinity it goes to negative pi by 2. But if I say that I tell you I have an input at omega equal to omega naught, where let's say I know that mod of H of j omega is, let's say 2 by 3, right? I'm just taking some number out of the hat, and here this is some phi now, some phi omega naught. Okay, so what will be your output if the input is, so if input is cosine omega naught t, what will be your output? Your output will be simply, if I just look into this waveform, I have to read out the value of, right? Read out the value of mod of H of j omega at omega naught and the phase at phi omega naught, right? Because note that, what is this telling us? The output will also be a cosinusoid of the same frequency omega, right? But it will be scaled in amplitude and shifted in time. And how do I know how much it will get scaled and how much will it get shifted? I can get it from this frequency plot, right? So what is it telling us? It is basically now telling us at omega naught I have some magnitude to 2/3. So I can basically say the output is 2/3 cosine omega naught t. I do not have to worry about omega naught because the output will also have the same frequency as input, right? And phi will be phi at omega naught, right? So again, extremely simple concept, but important to realize that we will be using this concept without even blinking an eye in couple of lectures from now. So it is very important to understand what is actually meant by a transfer function, right? Again, I am not going into the details of how you write out Fourier transforms and why how the transfer function equation comes. I assume that we are all familiar with it. Okay, so what are the key takeaways? The key takeaways till now in this lecture is, in an LTI system, if input is e⁻ omega naught t, output is a scaled version of e⁻ omega naught t, which means the natural outcome of this is an LTI system cannot change the frequency of the input, because the output is just a scaled version, scaled and shifted. The frequency doesn't change. Extremely important concept. So what does it mean then? Why is it important? It is important because now I'll take you back to previous lecture where I said that your input, let's say, is cosine omega naught t, right? So in frequency domain, what does it look like? Your input will be a tone at omega naught and a tone at minus omega naught of value. This will be delta direct function of value 1, right? The area should be 1. And if I say that your output, your h of j omega, let me simply write it as h of j omega. If I know that, let me just draw the mod of h of j omega, right? If I know that the mod of h of j omega is maybe something like this, then what will be the output? What will be the output? The output will essentially be, I will just align these two plots, right? So this is B naught. I'll just align these two plots and find out whatever is the value at this point, right? And the output will be again a tone at omega naught, right? And scaled by mod of j omega naught, right? Here also scaled by mod of h of j omega naught, right? And if you have an input, right? If you have an input, let's say at cosine twice omega naught t, simultaneously, let's say you have an input at cosine omega naught t, what will it mean? I'll essentially say that there is another tone at 2 omega naught, similarly a tone at minus 2 omega naught. What will be the output then? The output will be again a tone at 2 omega naught right? A tone at 2 omega naught, but what will be the strength of the tone? The strength of the tone will be value of the transfer function at 2 omega naught, right? Similarly, you are going to have something here. So this is the value of the transfer function at minus 2 omega naught. Okay, so I'll just mark it at here. This is h of 2j omega naught. This is h mod of h of j. So I can basically read out the output if I have the transfer function plots, as long as the input is a sinusoid, right, or a cosinusoid. Okay, so that is the beauty of dealing with this kind of plots. Okay, so before we end today's refresher, note that we have been talking about LTI system. We have been revising LTI system. But what about if the input is not an LTI system? When I essentially mean is that, I mean, when I say what do I mean, what is not an LTI system? Let me simply give you an example of a multiplier, right? So the input, let's say, is e to the power j omega naught t, and the output, let's say, is time varying, or not. Beg your pardon. So let's say the another input. I have two inputs. One is e to the power j omega naught t, and the other input is some x of t. X of t is time varying. What will be the output? So output will be e to the power j omega naught t times x of t, right? Easy peasy. But note that, is this a time varying system or a time invariant system? Firstly, is it a linear system? Sure, it's a linear system, because if I multiply the input by alpha, the output will also get multiplied by alpha. No problem, right? But what about if I shift the input? Let's say I give another input. I give e to the power j omega naught t minus t naught. I shift the input by t naught. What will happen to the output? Output will be e to the power j omega t minus t naught times x of t. Note that this is not the same as e to the power j omega naught t minus t naught times x of t minus t naught, right? So this is not a time variant. This is not an LTI system, right? This is not a time invariant system. So what is the impact of that? What is the impact of that in signal processing? The impact of that is, you can immediately understand. So let's say your input is, let me take a special case where the input is e to the power j omega naught t, and here this is something else. It's another complex exponential, e to the power j omega lt, right? So what is the output now? The output will be e to the power j omega naught plus omega lt, right? So what is the frequency of the input, right? So I should maybe be careful and say that this box is your system now. This box is your system, and the input is e to the power j omega naught t, right? So the frequency of the input is omega naught. The frequency of the output is omega naught plus omega L, right? So note that there is a frequency change. Sorry, there is a frequency change, right? So this is the case where when you have time variant systems, when system is no longer time invariant, you can have change in the frequency between the input and the output, right? And this is again, this has severe consequences, both positive and negative, in RF chains, and we are going to talk about it, some of it in the next class, and then take it from there. Okay, this topic. Thank you.